हेलो स्टूडेंट्स, आज हम फिज़िक्स का चैप्टर रीड करेंगे इलेक्ट्रिक चार्जेस एंड फील्ड्स। पार्ट 1 का वीडियो ऑलरेडी अपलोड किया हुआ है, आप प्लेलिस्ट में जाके उसे चेक कर सकते हो। ये एक ऑडियो बुक है, इसमें किसी भी प्रकार का एक्सप्लेनेशन नहीं है। एग्जाम्पल 1.1, हाउ कैन यू चार्ज अ मेटल स्फीयर पॉजिटिवली विदाउट टचिंग इट। सॉल्यूशन: Figure 1.5a shows an uncharged metallic sphere on an insulating metal stand. Bring a negatively charged rod close to the metallic sphere as shown in figure 1.5b. As the rod is brought close to the sphere, the free electrons in the sphere move away due to repulsion and start piling up at the farther end. The near end becomes positively charged due to deficit of electrons. This process of charge distribution stops when the net force on the free electrons inside the metal is 0. Connect the sphere to the ground by a conducting wire. The electrons will flow to the ground while the positive charges at the near end will remain held there due to the attractive force of the negative charges on the rod, as shown in figure 1.5c. Disconnect the sphere from the ground. The positive charge continues to be held at the near end, in bracket figure 1.5d. Remove the electrified rod. The positive charge will spread uniformly over the sphere as shown in figure 1.5e. In this experiment, the metal sphere gets charged by the process of induction and the rod does not lose any of its charge. Similar steps are involved in charging a metal sphere negatively by induction by bringing a positively charged rod near it. In this case, the electrons will flow from the ground to the sphere when the sphere is connected to the ground with a wire. Can you explain why? 1.5 Basic properties of electric charge. We have seen that there are two types of charges, namely positive and negative, and their effects tend to cancel each other. Here we shall now describe some other properties of the electric charge. If the sizes of charged bodies are very small as compared to the distance between them, we treat them as point charges. All the charge contained of the body is assumed to be concentrated at one point in space. 1.5.1 Additivity of charges. We have not as yet given a quantitative definition of a charge. We shall follow it up in the next section. We shall tentatively assume that this can be done and proceed. If a system contains 2 point charges Q1 and Q2, the total charge of the system is obtained simply by adding algebraically Q1 and Q2, that is, charges add up like real numbers or they are scalars like the mass of a body. If a system contains n charges Q1, Q2, Q3 and Qn, then the total charge of the system is Q1 plus Q2 plus Q3 and so on Qn. Charge has magnitude but no direction, similar to the mass. However, there is one difference between mass and charge. Mass of a body is always positive, whereas a charge can be either positive or negative. Proper signs have to be used while adding the charges in a system. For example, the total charge of a system containing 5 charges plus 1, plus 2, minus 3, plus 4 and minus 5 in some arbitrary unit is plus 1, plus 2, plus minus 3, plus 4, plus minus 5 is equals to minus 1 in the same unit. 1.5.2 Charge is conserved. We have already hinted to the fact that when bodies are charged by rubbing, there is transfer of electrons from one body to the other. No new charges are either created or destroyed. A picture of particles of electric charge enables us to understand the idea of conservation of charge. When we rub two bodies, what one body gains in charge, the other body loses. Within an isolated system consisting of many charged bodies, due to interactions among the bodies, charges may get redistributed, but it is found that the total charge of the isolated system is always conserved. Conservation of charge has been established experimentally. It is not possible to create or destroy net charge carried by any isolated system, although the charge carrying particles may be created or destroyed in a process. Sometimes nature creates charged particles. A neutron turns into a proton and an electron. The proton and electron thus created have equal and opposite charges, and the total charge is 0 before and after the creation. 1.5.3 Quantization of charge. Experimentally, it is established that all free charges are integral multiples of a basic unit of charge denoted by E. Thus, charge Q on a body is always given by Q is equals to NE, where N is any integer, positive or negative. This basic unit of charge is the charge that an electron or proton carries. By convention, the charge on an electron is taken to be negative. Therefore, charge on an electron is written as minus E and that on a proton as plus E. The fact that electric charge is always an integral multiple of E is termed as quantization of charge. There are a large number of situations in physics where certain physical quantities are quantized. The quantization of charge was first suggested by the experimental laws of electrolysis discovered by English experimentalist Faraday. It was experimentally demonstrated by Millikan in 1912. In the international system of units, a unit of charge is called a coulomb and is denoted by the symbol C. A coulomb is defined in terms the unit of electric current, which you are going to learn in a subsequent chapter. In terms of this definition, 1 coulomb is the charge flowing through a wire in 1 second if the current is 1 ampere. In bracket, see chapter number 2 of class 11 physics textbook part 1. In this system, the value of the basic unit of charge is E is equals to 1.602192 into 10 raised to minus 19 coulomb. Thus, there are about 6 into 10 raised to 18 electrons in a charge of minus 1 coulomb. In electrostatics, charges of this large magnitude are seldom encountered, and hence we use smaller units. 1 microcoulomb is equals to 10 raised to minus 6 coulomb, or 1 millicoulomb is equals to 10 raised to minus 3 coulomb. If the protons and electrons are the only basic charges in the universe, all the observable charges have to be integral multiples of E. Thus, if a body contains N1 electrons and N2 protons, the total amount of charge on the body is N2 into E plus N1 into minus E is equals to N2 minus N1 E. Since N1 and N2 are integers, the difference is also an integer. Thus, the charge on any body is always an integral multiple of E and can be increased or decreased also in steps of E. The step size E is, however, very small because at the microscopic level we deal with charges of a few microcoulomb. At this scale, the fact that charge of a body can increase or decrease in units of E is not visible. The grainy nature of the charge is lost and it appears to be continuous. This situation can be compared with the geometrical concepts of points and lines. A dotted line viewed from a distance appears continuous to us but is not continuous in reality. As many points very close to each other normally give an impression of a continuous line, many small charges taken together appear as a continuous charge distribution. At the macroscopic level, one deals with charges that are enormous compared to the magnitude of charge E. Since E is equals to 1.6 into 10 raised to minus 19 coulomb, a charge of magnitude say 1 microcoulomb contains something like 10 raised to 13 times the electronic charge. At this scale, the fact that charge can increase or decrease only in units of E is not very different from saying that charge can take continuous values. Thus, at the macroscopic level, the quantization of charge has no particle consequence and can be ignored. At the microscopic level, where the charges involved are of the order of a few tens or hundreds of E, that is, they can be counted, they appear in discrete lumps, and quantization of charge cannot be ignored. It is the scale involved that is very important. Example 1.2. If 10 raised to 9 electrons move out of a body to another body every second, how much time is required to get a total charge of 1 coulomb on the other body? Solution. In 1 second, 10 raised to 9 electrons move out of the body. Therefore, the charge given out in 1 second is 1.6 into 10 raised to minus 19 into 10 raised to 19 coulomb is equals to 1.6 into 10 raised to minus 19 coulomb. The time required to accumulate a charge of 1 coulomb can then be estimated to be 1 coulomb divided by, in bracket, 1.6 into 10 raised to minus 10 coulomb per second is equals to 6.25 into 10 raised to 9 second is equals to 6.25 into 10 raised to 9 divided by 365 into 24 into 3600 years is equals to 198 years. Thus, to collect a charge of 1 coulomb from body from which 10 raised to 9 electrons move out every second, we will need approximately 200 years. 1 coulomb is therefore a very large unit for many practical purposes. It is, however, also important to know what is roughly the number of electrons contained in a piece of 1 cubic centimeter of a material. A cubic piece of copper of one side 1 centimeter contains about 2.5 into 10 raised to 24 electrons. Example 1.3. How much positive and negative charge is there in a cup of water? Solution. Let us assume that the mass of 1 cup of water is 250 gram. The molecular mass of water is 18 gram. Thus 1 mole is equals to 6.02 into 10 raised to 23 molecules of water is 18 gram. Therefore, the number of molecules in 1 cup of water is 250 by 18 into 6.02 into 10 raised to 23. Each molecule of water contains 2 hydrogen atoms and 1 oxygen atom, that is 10 electrons and 10 protons. Hence, the total positive and total negative charge has the same magnitude. It is equal to 250 by 18 into 6.02 into 10 raised to 23 into 10 into 1.6 into 10 raised to minus 19 coulomb is equals to 1.34 into 10 raised to 7 coulomb. 1.6 Coulomb's law. Coulomb's law is a quantitative statement about the force between 2 point charges. When the linear size of charged bodies are much smaller than the distance separating them, the size may be ignored and the charged bodies are treated as point charges. Coulomb measured the force between 2 point charges and found that it varied inversely as the square of the distance between the charges and was directly proportional to the product of the magnitude of the two charges and acted along the line joining the two charges. Thus, if 2 point charges Q1 and Q2 are separated by a distance r in vacuum, the magnitude of the force F between them is given by F is equals to K in modulus Q1 Q2 by r square. How did Coulomb arrive at this law from his experiments? Coulomb used a torsion balance for measuring the force between two charged metallic spheres. When the separation between two spheres is much larger than the radius of each sphere, the charged spheres may be regarded as point charges. However, the charges on the spheres were unknown to begin with. How then could he discover a relation like equation 1.1? Coulomb thought of the following simple way. Suppose the charge on a metallic sphere is Q. If the sphere is put in a contact with an identical uncharged sphere, the charge will spread over the two spheres. By symmetry, the charge on each sphere will be Q by 2. Repeating this process, we can get charges Q by 2, Q by 4, etc. Coulomb varied the distance for a fixed pair of charges and measured the force for different separations. He then varied the charges in pairs, keeping the distance fixed for each pair. Comparing forces for different pairs of charges at different distances, Coulomb arrived at the relation, equation 1.1. Coulomb's law, a simple mathematical statement, was initially experimentally arrived at in the manner described above. While the original experiments established it at a macroscopic scale, it has also been established down to subatomic level. R is equivalent to 10 raised to minus 10 meter. Coulomb discovered his law without knowing the explicit magnitude of the charge. In fact, it is the other way round. Coulomb's law can now be employed to furnish a definition for a unit of charge. In the relation equation 1.1, k is so far arbitrary. We can choose any positive value of k. The choice of k determines the size of the unit of charge. In SI units, the value of k is about 9 into 10 raised to 9. The unit of charge that results from this choice is called a coulomb, which we defined earlier in section 1.4. Putting this value of k in equation 1.1, we see that for q1 is equals to q2 is equals to 1 coulomb, comma r is equals to 1 meter, F is equals to 9 into 10 raised to 9 Newton. That is, 1 coulomb is the charge that when placed at a distance of 1 meter from another charge of the same magnitude in vacuum experiences an electrical force of repulsion of magnitude 9 into 10 raised to 9 Newton. 1 coulomb is evidently too big a unit to be used. In practice, in electrostatics, one uses smaller units like 1 millicoulomb or 1 microcoulomb. The constant k in equation 1.1 is usually put as k is equals to 1 upon 4 pi epsilon 0 for later convenience, so that Coulomb's law is written as F is equals to 1 upon 4 pi epsilon 0 in modulus q1 q2 upon r square. Epsilon 0 is called the permittivity of free space. The value of epsilon 0 in SI unit is epsilon 0 is equals to 8.854 into 10 raised to minus 12 Coulomb square upon Newton meter square. Since force is a vector, it is better to write Coulomb's law in the vector notation. Let the position vectors of charges q1 and q2 be r1 and r2 respectively. See figure 1.6a. We denote force on q1 due to q2 by F12 and force on q2 due to q1 by F21. The 2-point charges q1 and q2 have been numbered 1 and 2 for convenience, and the vector leading from 1 to 2 is denoted by r21. r21 is equals to r2 minus r1. In the same way, the vector leading from 2 to 1 is denoted by r12. r12 is equals to r1 minus r2 is equals to minus r21. The magnitude of the vectors r21 and r12 is denoted by r21 and r12 respectively. In bracket, r12 is equals to r21. The direction of a vector is specified by a unit vector along the vector. To denote the direction from 1 to 2, we define the unit vectors. r21 caret is equals to r21 by r21, comma r12 is equals to r12 by r12, comma r21 caret is equals to r12 caret. Coulomb's force law between 2-point charges q1 and q2 located at r1 and r2 is then expressed as F21 is equals to 1 upon 4 pi epsilon 0 q1 q2 upon r square 21 r21 caret. Some remarks on equation 1.3 are relevant. Equation 1.3 is valid for any sign of q1 and q2, whether positive or negative. If q1 and q2 are of the same sign, in bracket either both positive or both negative, F21 is along r21 caret, which denotes repulsion, as it should be for like charges. If q1 and q2 are of opposite signs, F21 is along minus r21 caret is equals to r12 caret, which denotes attraction, as expected for unlike charges. Thus, we do not have to write separate equations for the cases of like and unlike charges. Equation 1.3 takes care of both cases correctly. In bracket figure 1.6b. The force F12 on charge q1 due to charge q2 is obtained from equation 1.3 by simply interchanging 1 and 2. That is, F12 is equals to 1 upon 4 pi epsilon 0 q1 q2 by r square 12 r12 caret is equals to minus F21. Thus, Coulomb's law agrees with the Newton's third law. Coulomb's law in bracket equation 1.3 gives the force between two charges q1 and q2 in vacuum. If the charges are placed in matter or the intervening space has matter, the situation gets complicated due to the presence of charged constituents of matter. We shall consider electrostatics in matter in the next chapter. Example 1.4. Coulomb's law for electrostatic force between 2 point charges and Newton's law for gravitational force between two stationary point masses. Both have inverse square dependence on the distance between the charges or masses. A. Compare the strength of these forces by determining the ratio of their magnitudes. First, for an electron and a proton, and second for the protons, for two protons. B. Estimate the accelerations of electron and proton due to the electrical force of their mutual attraction when they are 1 angstrom in bracket 10 raised to minus 10 meter apart. In bracket, mass of proton is equals to 1.67 10 raised to into 10 raised to minus 27 kg, and mass of electron is equals to 9.11 into 10 raised to minus 31 kg. Solution. A. First part. The electric force between an electron and a proton at a distance r apart is Fe is equals to minus 1 upon 4 pi epsilon 0 E square upon r square, where the negative sign indicates that the force is attractive. The corresponding gravitational force is Fg is equals to minus g mp into me upon r square, where mp and me are the masses of a proton and an electron respectively. In modulus, Fe upon Fg is equals to E square upon 4 pi epsilon 0 g mp into me is equals to 2.4 into 10 raised to 39. Second, on similar lines, the ratio of the magnitudes of electric force to the gravitational force between two protons at a distance r apart is, in modulus, Fe upon Fg is equals to E square upon 4 pi epsilon 0 g mp into mp is equals to 1.3 into 10 raised to 36. However, it may be mentioned here that the signs of the two forces are different. For two protons, the gravitational force is attractive in nature and the Coulomb force is repulsive. The actual values of these forces between two protons inside the nucleus in bracket distance between two protons is approximate 10 raised to minus 15 meter inside a nucleus. Rfe approximate 230 Newton, whereas Fg approximate 1.9 into 10 raised to minus 34 Newton. The dimensionless ratio of the two forces shows that electrical forces are enormously stronger than the gravitational forces. B. The electric force F exerted by a proton on an electron is same in magnitude to the force exerted by an electron on a proton. However, the masses of an electron and a proton are different. Thus, the magnitude of forces in modulus F is equals to 1 upon 4 pi epsilon 0 E square upon r square is equals to 8.987 into 10 raised to 9 Newton meter square upon Coulomb square. 1.6 10 raised to minus 19 Coulomb square whole square upon 10 raised to minus 10 whole square is equals to 2.3 into 10 raised to minus 8 Newton. Using Newton's second law of motion, F is equals to ma, the acceleration that an electron will undergo is A is equals to 2.3 into 10 raised to minus 8 Newton upon 9.11 into 10 raised to minus 31 kg is equals to 2.5 into 10 raised to 22 meter per second square. Comparing this with the value of acceleration due to gravity, we can conclude that the effect of gravitational field is negligible on the motion of electron and it undergoes very large accelerations under the action of Coulomb's force due to a proton. The value for acceleration of the proton is 2.3 into 10 raised to minus 8 Newton upon 1.67 into 10 raised to minus 27 kg is equals to 1.4 into 10 raised to 19 meter per second square. Example 1.5. A charged metallic sphere A is suspended by a nylon thread. Another charged metallic sphere B held by an insulating bundle is brought close to A such that the distance between their centers is 10 cm as shown in figure 1.7a. The resulting repulsion of A is noted in bracket, for example, by shining a beam of light and measuring the deflection of its shadow on a screen. Spheres A and B are touched by uncharged spheres C and D respectively as shown in figure 1.7b. C and D are then removed and B is brought closer to A to a distance of 5 cm between their centers as shown in figure 1.7c. What is the expected repulsion of A on the basis of Coulomb's law? Spheres A and C and spheres B and D have identical sizes. Ignore the size of A and B in comparison to the separation between their centers. Solution. Let the original charge on sphere A be Q and that on B be Q dash at a distance r between their centers. The magnitude of the electrostatic force on each is given by F is equals to 1 upon 4 pi epsilon 0 Q dash upon r square. Neglecting the sizes of spheres A and B in comparison to r, when an identical but uncharged sphere C touches A, the charges redistribute on A and C, and by symmetry each sphere carries a charge Q by 2. Similarly, after D touches B, the redistributes charges on each is Q dash by 2. Now, if the separation between A and B is half, the magnitude of the electrostatic force on each is F dash is equals to 1 upon 4 pi epsilon 0 Q by 2 into Q dash by 2 upon R upon 2 square is equals to 1 upon 4 pi epsilon 0 Q dash upon R square is equals to F. Thus, the electrostatic force on A due to B remains unaltered.